I am Prashant from Sri Venkateshwara College of Engineering, second year, fourth sem. Today we are going to learn about permutation groups. Introduction to permutation groups. Permutation groups are mathematical structures that describe the arrangements of elements. They play a crucial role in various fields including algebra, combinatorics, and group theory. Understanding permutation groups helps in solving problems related to symmetry and structure. Definition of permutations. A permutation is a rearrangement of the elements of a set. The number of permutations of a set with n elements is n. Permutations can be represented in cycle notation for easier manipulation. Basic theory of group theory. A group is a set of equipped with a binary operation that satisfies certain properties. The elements of a permutation groups can be combined through function composition. Groups must satisfy closure, associative, identity, and inversibility. The basic group theory are divided into 7 parts: basic definition and simple examples. Further examples: subgroup, the rearrangement lemma and the symmetric group, classes and invariant subgroups, Hosters and factors groups, homonyms, direct products. Notation and terminology. The symmetric group of n elements is denoted as Sn. The order of group is the number of elements it contains. Subgroups are smaller groups contained within a larger group. Examples of permutations groups. A symmetric group S3 consists of all permutations of 3 elements. The alternating group A3 is a subgroup of S3 containing given permutations. Other examples including S4, S5 are larger symmetric groups. Cycle notation. Cycle notation describes permutations compactly by grouping elements in cycles. For instance, the permutation 1, 2, 3 means 1 goes to 2, 2 goes to 3, 3 goes to 1. This notation aids in visualizing how elements are rearranged. Properties of permutations. Permutations can be classified as even or odd based on the number of transpositions. Even permutations can be expressed as an even number of swaps. Understanding these properties is vital for analyzing permutation groups. Composition of permutations. The composition of two permutations is performed by applying one after the another. This operation is associative, meaning the order in which permutations are combined matters. The identity permutation leaves all elements unchanged when composed with other permutation. Subgroups of permutation groups. A subgroup is a group formed after a subset of larger number, a group. The alternating group is a significant subgroup of the symmetric group Sn. Subgroups helps in understanding the structure and classification of permutation groups. The alternating group. The alternating group consists of all permutations of n elements. Its order is n factorial by 2, reflecting the half of the total permutations that are even. N is a normal subgroup of Sn and plays a crucial role in group theory. Cayley's theorem. Cayley's theorem states that every group is isomorphic to a subgroup of a symmetric group. This theory illustrates the universality of permutations groups in group theory. It allows for abstract groups to be represented concretely through permutations. Generating permutation groups. A permutation group can be generated by a set of permutations called generators. Generators can be used to construct all elements of group through composition. Understanding generators aids in exploring the structure of permutation groups. Application in combinatorics. Permutation groups are fundamental in counting problems and com- combinatorial designs. They help in understanding symmetries in various mathematical structures. Applications extend to fields like cryptography and error connecting codes. Applications in physics. In physics, permutation groups helps describe symmetries in practical interactions. They are used in the theories such as quantum mechanics and string theory. The role of symmetry in physical laws is a crucial area of research. Representation theory. Representation theory studies how groups can be represented through matrices. Permutation groups can be represented through permutation matrices. This area connects abstract algebra with linear algebra and has numerous applications. Computational aspects. Algorithms exist for generating and manipulating permutation groups efficiently. Computational group theory focuses on the study of groups using computational tools. This field has significant implications for solving problems in mathematics and computer science. Permutation group actions. A group action describes how a group interacts with a set by permuting its elements. Understanding actions helps to analyze the structure and properties of groups. Orbit stabilizer theorem is a key result in this area, relating group actions to cosets. Advanced topics in permutation groups. Topics like conjugacy classes and normal subgroups are vital in deeper studies. Advanced topics includes the classification of finite simple groups. This concept further enriched the understanding of the interplay between group theory and permutations. Research directions. Current research in permutation groups includes exploring their algebraic properties in investigating connections with other mathematical fields such as topology is ongoing. Studying the computational aspects continues to evolve with technology advancements. Finally, the conclusion. Permutation groups are a foundational concept in modern mathematics. They bridge various mathematical disciplines and have rich applications. Understanding permutation groups provides valuable insights into the structure of mathematics. Feel free to customize any specific content or area